Hey guys, today we are talking about liquid-liquid extraction in bioseparations. So, the overall main process of what's happening in liquid-liquid extraction is we have a feed stream containing media, and then we have a solvent that are mixed, and we want them to separate. So, the compound we want is the solute, that's our product. Whereas the solvent can contain some portion of the desired product, but depending on how much we want to separate it, it's either going to be a smaller amount or a larger amount, depending on how many units we have.
Some of the equations we have are the distribution coefficient and the extraction factor, which can be used when solving single and multi-stage extraction problems. And we also have the rejection ratio and the percent of solute extracted, which can only be used for multi-unit processes. The distribution coefficient is the ratio of the concentrations of solute in the light phase, YL, compared to that in the heavy phase, XH. The extraction factor is the ratio of the total mass of a solute in the extract to that in the other phase. The rejection ratio is the weight ratio of the solute, which is our product, leaving in the light phase compared to that leaving in the heavy phase. The percent of solute extracted is the amount of solute extracted through the number of stages that there are.
In a single unit liquid-liquid extractions, you have to make some assumptions. Those assumptions are Kd is constant, both fluids are immiscible, we are extracting from heavy phase into light phase, input flow rate for heavy phase is equal to the output flow rate for heavy phase, and the input flow rate for light phase is equal to the output flow rate for light phase.
For multi-unit countercurrent liquid-liquid extraction, it's really similar to the single unit, but with just more stages. We have our feed stream going in one way and then our extract going the other way. You can see highlighted that Y1 and X1 should be in equilibrium if we are assuming an ideal separation. And this is going to give us a higher purified product with a better separation.
Alright, so now we're going to look at an example problem. Here we see that E. coli was engineered to produce 20 grams per liter of propionic acid in a CSTR. We're given a feed flow rate of 1,000 liters per hour and told that methyl isobutyl ketone is utilized to extract the propionic acid from the fermentation broth. We're given the equilibrium relationship of Ce equals 2.15 Cr. Ce is that concentration in the extract, and then Cr is the concentration in the raffinate. And then we are also told that the solvent enters at 200 liters per hour. We'll look at two parts for this problem. Part A, what fraction is extracted if we use one separation unit, and then B, how many stages are necessary for 99% extraction. For part A, for that single unit process, we'll use the relationship between Ce and Cr to find our Kd through our YL and XH relationship. And then we can use the E equals LKD over H equation to solve for E with those numbers and our given flow rates. We find an E of 0.43, and then we can use that and our relationship between X1 and X0 to find a relationship of 0.7 between X1 and X0, and then we can use our mass balances to find their respective concentrations, and then we'll divide the Y1 6 grams per liter over the original 20 grams per liter for a 30% extraction. And then for part B, the multi-stage process, we will use our percent extracted, which we know is 99%, equal to the 1 minus 1 over R plus 1. We'll find an R rejection ratio of 99, and then we'll set that equal to our equation to solve for number of stages. But because we have an E of less than 1, we will actually get an undefined N. It'll be like using a negative base in a log. So that means that because we have an E less than 1, we actually cannot reach our target percent extraction.
Some real-world examples are the production of perfumes, diesel, and vegetable oil.
Alright guys, thanks for watching. Leave some questions for us in the comments. Hit that like button, subscribe for more awesome content, and always nerds, stay curious.